Thank you for the introduction. Yeah, I would like to talk about multiple zeta values and algebraic structures on them. So what I like to start first with is a very general approach to Hopf algebra structures, or more precisely, what techniques I use to get Hopf algebra structures. But I promise it will be not too long until we get to the multiple zeta value part, which is maybe more related to what is going on in this conference. So the first part is about post-Lie algebras. To make it a bit easier and simpler to write, I will just consider 3 Lie algebras, though anything will remain correct on arbitrary Lie algebras, which means by Lie S from now on I will denote 3 Lie algebra on the set S, or sometimes also called alphabet S or whatever. So it means it's just generated by all possible brackets you can build out of the elements in S. Whenever I have such a 3 Lie algebra given, then a post-Lie structure on it is the following. It's a bilinear map, usually denoted by such a triangle. Product, so lives on product with the Lie algebra with itself. And it's on the 3 Lie algebra S, so I should impose certain compatibility conditions with the bracket on it. And this is as follows. So the first one is that this thing for any x should be a derivation, which means if I write now a Lie bracket y and z, then this should be equal to x triangle y, z plus y, x triangle z. And there's one second condition which goes the other way around. So now I want to say what happens if I have a Lie bracket here. And here it looks a bit tedious, but it's the definition which seems to work. So I have this triangle composition minus the same one where I switched the bracket. And then I have two more terms where y and x are not. So sometimes it's also called obstruction from associativity, because as soon as it would be associative, this would be always 0. Any x, y, and z in this Lie algebra. And maybe because I will probably use this terminology, then usually this triple consisting of the space, its bracket, and this triangle is what people call a post-Lie algebra. Yeah, because of my next line, because whenever you have a post-Lie algebra, you can build a second Lie algebra afterwards. So this is where this post comes from, I guess. And this works as follows. So usually you use curly brackets now, and then this curly bracket of x and y corresponding to this triangle defined as x triangle y minus y triangle x plus the usual old bracket of x and y. And the claim is now this is a new Lie algebra you get afterwards out of it. So Lie S equipped with this bracket is a Lie algebra. So it's clear that it preserves the space because all of it is defined on it. So the only thing you have to check is that's really a Lie bracket, so it satisfies antisymmetry and Jacobi's identity. And antisymmetry should be hopefully quite clear from this definition, that you can exchange x and y for a sign. And then Jacobi's identity, this is what you get out of the compatibility conditions. So they are exactly built in a way that this always works. Okay, so far I have a Lie algebra structure, so somewhere I have to come to Hopf algebras. But this is maybe not too hard because whenever you have a Lie algebra, you can consider its universal enveloping algebra, and this will naturally come with a Hopf algebra structure. Consider the universal enveloping algebra, and now we can make use of it that we just considered a free Lie algebra, because now the universal enveloping algebra, what we usually denote by this thing, I'm not sure how common this notation is. So this is just the free non-commutative algebra on S, which means the product is concatenation of words or monomials, whatever language you use, and the coproduct. This should be dual. So we need what I usually denote by delta shuffle to make clear it's dual to the shuffle product. And this is the one where all elements in S are primitive, and then you extend by concatenation. This is the basic, or maybe most basic Hopf algebra structure I think you can get on this non-commutative free stuff. Okay, so this is the basic one. And we, maybe as we change the Lie bracket on S from the trivial one to another one, we want to do the same here. And this we do by defining a new product. So on this universal enveloping algebra, we define Grossman-Larson product. Follows. So if I have something in the universal enveloping algebra and want to multiply it, the sum of A1's, A2's triangle B. So maybe I have to explain this notation. So this A1 and A2 just come from the Sweetler notation. So what you do, you take the coproduct I have on QS and then just write it as the product of A1 tensor A2. So this is just a notation thing. And maybe also the triangle is not completely clear because so far I just defined it on this free Lie algebra, but now I apply it to elements in the universal enveloping algebra. But there's a very technical statement that you have an extension which has certain conditions and which is nice, but I think which will not help us if I give you all the details now. But it can be extended to this whole thing. And then you have a well-defined product, not coproduct. Okay, so the last statement, which finishes maybe this general section, if I take now this Q of S, equip it with the Grossman-Larson product, and still the coproduct from before, and this is the Hopf algebra. Maybe I should put names here, but unfortunately they all have long names. So this was proven by Ibrahimi, Montekas, and Lunderwold. So just to make sure what's going on here. So if I usually have a free Lie algebra and take the universal enveloping algebra, I will get concatenation here, and it's more or less trivially a Hopf algebra. And the whole point is now, I don't take the usual bracket, but I take this new curly bracket. And if I build out the universal enveloping algebra, then I will exactly get this Grossman-Larson product, and then the point is it must be a Hopf algebra. There is a recursive construction, but it's not very nice and not computable in general. It very much depends on what you started with, whether you can compute it or not. So maybe I should mention this, but the formula is not nice, so I will not show this to you. You can also, if you have good enough space, for example, with a grading or something, dualize the space, and then you can also get a formula for the coproduct dual to this product. But I will just show you an example, maybe somehow, how it looks like. So this was the very general story. So the second part is an example. And the example will be the Ihara bracket, which I guess at least some of you should or have seen before. So I want to consider it on a very specific set, namely on the two-letter thing consisting of x0, x1. And I think if you know about multiple zeta values, you can already guess in which direction it goes. And the triangle is defined as follows. So whenever I have any f now in the freely algebra on this two-letter thing, then the triangle, maybe I put an I here for Ihara to distinguish it from the general case, and apply it to x0, it should be 0. And if I apply it to x1, it should be the commutator of x1 and f. And then the first condition up there tells me what I do on any other more general thing here. I can extend it as a derivation. And it's really not too hard to check. This is why I can also not give a name for this maybe. That this triple will be then a Postli algebra, so that both conditions are satisfied. So the first one is by definition, and the second one you just have to calculate. So in particular, now we can apply what we have done before, which means the first step is we get another Lie bracket on this freely algebra. Here maybe I omit the I because the usual notation for it is just curly brackets, which is really defined in the same way what I wrote before. And this is what people usually would call the Ihara bracket. So one more thing I want to show you. Now I have a bracket, so the next step would be the product. And this can be also calculated very precisely. A bit longer than the other formulas, but it will be the only one. So I hope it's fine. So whenever I take any element now in the universal enveloping algebra, so in this Q of x, then the Grossman-Larson product with the word looks as follows. So it makes a huge difference whether it's x0 or x1. So I'd like to order maybe my word for x0s and x non-zeros, means x1. So maybe the natural way how you would write monomials in the context of multiple zeta values. And then it's as follows. So you again have the sum which comes from the coproduct notation. Then you have the first coproduct factor of this W. All the x0s stay untouched. And then you get the next coproduct factor. You get the antipode of the next coproduct factor. then you have the x1, then you have the third antipode factor, which means I do not just apply the coproduct once, but as often as I want. It's co-associative, so it doesn't matter where I apply it. So you get a chain of coproduct factors. And you put them always before and behind an x1. And now it matters whether it's before or behind if you put an antipode or not. So continues really like this. So the last one. So this is how it will look like. So you decompose W often enough to squeeze it in any position, but never between two x zeros. Okay, I mentioned this already as the antipode, but I should maybe also write it. I'm not sure. Here this is. It's the antipode for the usual Hopf algebra structure. So it will be just the reversing of the word with a sign. So what we just learned is this will give me a Hopf algebra structure. And what I should also mention, if I dualize this Grossman-Larson product for the Ihara bracket, then I get Goncharov's coproduct. If you've never heard about this coproduct, I think it's not too important, but this is a very maybe nice coproduct in the context of multiple zeta values. And you can really just combinatorically calculate the dual now and will end up with a formula for the Goncharov coproduct. Okay, so this was maybe the algebraic background, which means now I should explain how all of this is related to multiple zeta values. And this is all due to this Lie bracket, because this Lie bracket maybe occurs quite often. Definitely Ihara studied it. He studied some Galois action, or more precisely, the absolute Galois group acting on the fundamental group of P1 minus 3 points. But also some of you might know it's the Lie bracket on the Grothendieck-Teichmüller Lie algebra, which I guess from the title will occur in the next talk. And this is what I want to do, it occurs in the context of multiple zeta values. Okay, here I really had no idea how well-known multiple zeta values are. So I will give a very basic, but also quite short introduction. So if you all know about this, I'm sorry, this will be a bit boring the next 5 minutes. So the definition is as follows. Whenever I have positive integers, where the first one is strictly greater than 1, then the multiple zeta value is defined as follows. An infinite nested sum. What it shows, so n1 is the biggest one. 1 over n1 to the k1 up to nd to the kd. And these conditions here ensure that the series always converges. So this will be always some real number. Yes. I mean, the good thing is, if I have no x0 in the end, also all the terms will never have an x0 in the end, so you can restrict. But nevertheless, you can also regularize, so whatever you prefer. But all these structures, and especially the Lie algebra structure, must lie on the space where I allow x0 in the end. I cannot restrict, because then the space will be trivial. Okay, we have a weight. This is just the sum of the integers. And we have the space, which is spanned by all these multiple zeta. And the rough idea is mainly that we want this dual Hopf algebra structure on this space. So it's not that direct and perfectly working, but I like to explain how far this is possible. But to do so, I want to first introduce some basic properties of this algebra Z, because this will explain how the Lie algebra structure below it will be built. So the first very easy observation is this is not a vector space, this is an algebra. And the product is also very easy to describe if you don't want to give a general formula. Because the product idea is very simple. So if I just take Riemann zeta values, which means I just have those two terms. And the idea to multiply them is just to order the sums. So either I can take the ordering where n1 is strictly greater than n2, which is by definition then zeta of k1, k2. Or I can take the order where n2 is strictly greater than n1, which would be zeta of k2, k1. Or the last option would be that n1 and n2 agree. Then I can just add the exponents and get zeta k1 plus k2. And this is really everything you need to know about this product, because you can do the exact same thing which when you have two multiple zeta values. You just have to go for all ordering, how you can order these two indices into each other, such that each order is preserved. And this is what I want to call the shuffle product. So just to make clear how this is meant, I mean, here is just the multiplication of real numbers, roughly. So Staffel product really refers now to this one unique expression I get by this ordering procedure. I mean, there might be more, or there are more versions for the product. But this refers to this one. Yes. Yeah, usually I have to say that you invented it, but now you are here, so great. Okay, so we have one product, and the second main feature of multiple zeta values is that they are, and this is probably the part you know best, are iterated integrals. I assume that this is even more known, but just let me give you an example to make clear how this works. So for example, if you have zeta 2, 3, then it will be the following iterated integral. So first we treat the 2, which means we have one time this differential operator, dt1 over t1. And then the second one is dt2 over 1 minus t2. So this corresponds to the 2. And then we have to deal with the 3, which means we have 2 times this operator, and the last one will be again the last one, and that will be hopefully. And this is again extends very naturally now to any index you can think of here. Just take k minus 1 this differential form, and the last one will be always. So mainly I can play now the same game which I did before with the sums. If I want to multiply now two iterated integrals, the idea more or less stays the same, because it's just the integral over an ordered index. So if I multiply, I again put these index into each other, and what this will give me in the end is the shuffle product. And yeah, if I do this procedure on the iterated integral level and translate back into this notation, just to give you an example, in the smallest case, it would look like this. So it's a sum from 2 to k1 plus k2 minus 1. And then we have some binomial coefficients. And then we have zeta j, k1 plus k2 minus j. So we get a second product expression. Maybe just as a side remark, because we will not use it so much more, but both products are perfectly fine with the weight, so they are all weight homogeneous. Sure, but I thought for the conference it would be nice to have an iterated integral somewhere. But yeah, you can also get it combinatorically totally from the series. Okay. So let me give you one more example to really make clear how you get now relations in this algebra Z. The idea is really just to calculate this product now of in these two ways we have. So if I use Duffer, this term would be zeta 2, 3 plus zeta 3, 2 plus zeta 5. Or you use this formula, which means you have to evaluate this binomial coefficients. And what you would get is zeta 2, 3 plus 3 zeta 3, 2 plus 6 zeta 4, 1. And now you see some terms cancel. So what will survive is that zeta 5 is 2 zeta 3, 2 plus 6 zeta 4, 1. Okay, and there's a particular reason why I showed you this relations, because up to some maybe technical things, this is how you get all relations among multiple zeta values conjecturally. So let me make this a bit more precise. So this is what usually is called the double shuffle relations. And then one of the big main conjectures in this field is as follows. It's due to Ihara, Kaneko, and Sagi. Which states, if I take all the products I can and do this procedure, and I do some regularization process, which means I make somehow sense of the multiple zeta values where k1 is also allowed to be 1, and then play this game again. Then I get all relations in my algebra Z. I mean, sure, yeah, there you have pi. Okay, but what I want to do now is mainly using this conjecture, because this suggests me now a Lie algebra structure, or maybe a space where I have a Lie algebra structure on. So this Lie algebra is what is usually known as the double shuffle Lie algebra. So I introduced maybe most of it, but I need some notation to make it nice. Okay, so I still have this shuffle coproduct, which we have already seen. This should be okay. It's the one which sends x0 and x1. If you remember, this were those two letters to its primitive version. But to describe the shuffle product, I also need another alphabet, which is often denoted by y and consists of the letters y1, y2, y3, and so on. I can project from my qx to qy by just sending x0 to the n-1, x1 to yn, and then extend this with concatenation. And okay, and if there's an x0 in the end, there's nothing to do, so it just gets mapped to 0. Roughly, I just project the terms which n and x1. So with this projection, I can assign to any element in Q of x, element in Q of y, by having some correction term and then just the projection. This term, not too important, but lives just in the algebra on y1, and it just corrects this regularization stuff I haven't made precise anyway. And the last ingredient I need for this Lie algebra is also a coproduct on y. So this coproduct was dual to shuffle. So what I want here is a coproduct dual to the shuffle product. You can also make it precise because it's not too hard. On the letters, also has the primitive part. And then I have some part where I have sums. And then it extends with concatenation. And these are really all the ingredients I need to define the Lie algebra. So let dm0 be the space of all f in this Q of x, such that we have the following. So the coefficient of x0 and f, so this is my notation for the coefficient. And the coefficient of x1 and f should both vanish. Then we have some primitivity condition under the shuffle coproduct. And similarly, primitivity under the shuffle product, but before I have to shift f to the y alphabet. And finally, I have one more coefficient which vanishes. So let me maybe make clear why this is the correct space I want to consider. So my conjecture was the starting point, which was I just need double shuffle and regularization. So those are really the things I have to keep here in the Lie algebra. So I need the shuffle product, which is encoded just in this primitivity for the coproduct dual to shuffle. Then I have shuffle, and being algebra morphism with respect to shuffle, now really encoded in this primitivity condition. Then I have this plus regularization, which you mainly see here. And then I have this weird last condition, which I additionally have to impose to get a Lie algebra structure. So 1, 2, 3, reformulate the relations I inspect in Z, and the last condition is additionally, which means I have to go modulo zeta of 2. And there's the following theory, which was proven in the thesis of Racinet, which states that this dm0 equipped with the Ihara bracket, oh no, I put the I again, I want to omit it, is Lie algebra. So remember, this Ihara bracket was erased now, I guess. It lived on the free Lie algebra on X, and the second condition is totally equivalent to being in this Lie algebra. So this space is really a subspace, and then he was able to show that this bracket really preserves all these additional conditions, and especially for this one, it's not so easy to see. So again, using our somehow machinery behind, we get now that the universal enveloping algebra with this Grossman-Larson product we have seen, and the shuffle product, as well as its dual, which I denote by this V, equipped with shuffle then, and the co-product of Goncharoff, or maybe I write it like this, are Hopf algebra. Okay, and before I can conclude, maybe the circle, I have to clean the board once more. So I can reformulate now the conjecture more or less what's on the very end of this other blackboard. It just states that this thing is isomorphic to Z modulo zeta 2. So in particular, because we have a Hopf algebra structure here, as soon as this conjecture is true, we would get a Hopf algebra structure on multiple zeta values. So far, it's just known on formal or motivic ones. Usually, I just also say something about how the Grothendieck-Teichmüller Lie algebra relates to this stuff, but I guess this will be in the next talk, so I can omit this here. So for the last part of my talk, I want to explain this additional Q I had in my title. So the last part will be about multiple Q zeta values. Okay, let me shortly explain what Q means or what the Q analog is. For example, if I consider any positive integer, a Q analog is the following. It would be 1 minus Q to the n over 1 minus Q, or if you extend this geometric series. And it's a Q analog because if I take now the limit Q to 1, then I get 1 plus 1 plus 1 plus 1, so I just recover n. So that's the very basic toy example, but you can do this with any kind of stuff you like. You start with something, then you introduce something more general with a Q in it, and whenever you take the limit Q to 1, you get back what you started with. And I know I made brackets again. Of course, I don't want brackets here anymore. So, and this is what we want to do with multiple zeta values. We want to introduce something where we have no Q in it, Whenever I take the limit q to 1, I get back my multiple zeta values. And you might observe already that Q analogs are totally non-unique. There are a lot of polynomials which will be all go to n under the limit q to 1. And the same is true for multiple zeta values. This is one of the reasons why there are already several versions of Q analogs in the literature. So I will just show you one because I think time is not enough to show all of them. But there's one which we studied by Sudelin and Schlesinger independently. Those are defined for non-negative integers, where the last one is positive. And they look as follows. So they are also infinite sums. Then I have q to the n1 s1 over 1 minus q to the n1 s1 and so on. These are always our series in Q. Okay. So this is one version you could choose. And if you take the limit not q goes to 1, after multiplying with a certain factor of 1 minus q, it will be really give you the multiple zeta values. And we want to study the space as before, which is spanned by all these multiple zeta values. And again, the idea is somehow, as we did it for multiple zeta values, to get a Hopf algebra structure on it by doing very similar stuff. But before I continue, let me at least mention all the Q analogs we know are somehow contained in the space ZQ. So it's maybe not too bad to make this choice and consider this algebra. And maybe from a more modular aspect, you can also argue that this space captures the relations of multiple Eisenstein series. So you can also extend Eisenstein series to multiple versions as you extend the zeta function to multiple zeta values. And then some rational version of them also spans the space. So this is another point of view you could take here. Okay, so the problem is it seems to be much more difficult to do all this kind of stuff we have seen for multiple zeta values on this space. So what we have to do is somehow we have to simplify. And the simplification we want to do today is we want to consider the associated depth gradient. What do I mean by this? Very formal, but I hope it will be clear what it is. So it's a direct sum over the d filtered component modulo the d minus 1 filtered component, where these filtered components are with respect to the depth, which means this spanned by all these multiple q zeta values. There are minus the number of zeros smaller equal to d. So this is what we call the depth. So whenever you have a relation or a product or whatever, you just throw all the terms out which are not of highest depth, and this is how you will roughly get this depth graded version. Okay, I will not go through all the details again, what the relations are, how they look like, what we conjecture, but directly write down what the Lie algebra is and hope it will become more or less clear how the relations should look like. So this is what I call the linearized balanced Lie algebra. Okay. So it lives now on a new alphabet, denoted by B, and consists of the letters B0, B1, B2, and so on, somehow a merging of the alphabets X and Y for multiple zeta values. Maybe I don't read this one, but the other one. Okay, so we still have the shuffle co-product also on this alphabet B. This should be maybe fine. I mean, we still want to be somehow in this freely algebra stuff. And then there's one more operator, which lives on the subspace QB0, which is spanned by words not ending in B0. So this subspace really corresponds to the subspace where my multiple Q zeta values exist. So here I don't regularize. And on this subspace I have the involution tau, which maps B0 to the MBK to B0 to the K minus 1, the M plus 1. And then we extend this as an anti-morphism. Okay, so this list is hopefully at least already smaller as the one for the multiple zeta values, but it's already enough to introduce the Lie algebra. So I denote this now by LQ, and it's the space of all F now in QB, such that we have a very similar initial condition. The coefficient of B0 and F should vanish. I hope the second condition is not too surprising. We still want primitivity under the shuffle co-product because we want LQ to live inside of the freely algebra on B. Then I introduced tau, so I should do something with tau. And what I want to do is I would just want to require invariance. So pi 0 is the projection. So QB0. In the really naive sense. So if something ends in B, not in B0, it's fine, it's just the identity, and outside it just maps everything to 0. And then one last condition, also the coefficient of B0 to the M BK should vanish whenever K plus M is even. So this time I maybe omitted the background, but I hope it's somehow clear. So the structure we have on this associated depth-graded algebra is that elements multiply with respect to the shuffle product, and they are tau invariant. These are the main conditions on there. And then we just have some additionally regularization condition. And again, the last one is additional. So I have to mod out the terms also in the algebra. So these three reformulate. This is additional. And the observation is this space is a Lie algebra. And as before, I mean, this is why I introduced it in the beginning. The Lie bracket comes from a post-Lie structure. So the Lie bracket is also such a curly bracket, which means we have some triangle. Now I have to explain the triangle. But maybe before I do this, maybe just as a side remark, I have now an index A. This refers to the Ari bracket, which was introduced in Ecalle's weird long stuff. But I will make it explicit without any of these things. Namely, whenever I have any word I can define the triangle. Again, I just have to say what happens on the letters, because then it should extend as a derivation, because I want it to be a post-Lie structure. And on B0, it's very simple. And on any other BI, it's a bit more complicated. So I have a sum. Where I decompose the sum of the case. It's a bit tedious. Then I have some maybe coefficients, which are not too important. The only main important point is that these binomial coefficients bound the L's. The L's must be always smaller or equal to the K's. And then the term is maybe not too bad. I mean, I have this I, and add now this remaining term R. And any other K in my word I started with gets now replaced by this L. So maybe as a side remark, if I just take the letters B0, B1, all the summands become trivial, and what I recover is the Ihara bracket I had in the very beginning. So it's really a generalization of it. Okay, also here, we can complete now the picture. We have the Lie algebra structure, which means we get Hopf algebra structures with the Grossman-Larson product, or its dual. We have shuffle and the dual to the Grossman-Larson product. And those product and co-product you can really calculate totally explicitly, but already the bracket is maybe a bit lengthy, so these formulas will be quite long, so I think it doesn't make too much sense to write them down now, but they are totally explicit. And maybe now the way back to ZQ. So we have a projective algebra morphism. By construction from these Hopf algebra here onto the associated depth graded of ZQ. Again, the last condition was additional, so I have to mod out something here. I think if you are familiar with modular forms, you might guess what this could be. It's generated in way 2, 4, and 6, so you can think of it as quasi-modular forms. But the point is you have a surjection in this case, and the conjecture, but this is unproven so far, is really now that the coproduct and here this scans to a coproduct on this space. So it's compatible with all the additional relations. Okay, so in the last 2 minutes, I want to relate the two Lie algebras you have seen now. Because I think this is maybe the main advantage of this LQ. Namely, we have an injective Lie algebra morphism from this double shuffle Lie algebra we have seen before. I mean, I considered my algebra in the associated depth graded version. So to get something which is related, I also have to do it here. But if I do this, then I get an injection into LQ. The conjecture, the map is also not too hard. It's when I have any f, it maps to theta x of f plus theta y of pi y of f. So remember, pi was just the projection to the y alphabet, and this is really the map which sends xi to bi, and this is the map which sends yi to bi. So you can really easily embed the associated depth graded of the double shuffle Lie algebra into LQ. And the main advantage of this LQ is, at least for me, the shape seems to be nicer because you don't have to deal with a second coproduct and some regularization, comparison map and whatever. You just have this tau invariance, and tau is a very simple, I would say, linear map. So for me, it seems to be easier. And it's also not too hard to recover the image of this space inside here because of a very particular shape. And maybe just as a very small outlook, there's also some space here if I omit this associated depth graded. So I can make this space completely explicit. And there's also a formula for the Lie bracket, but there it's so far unproven whether it's really a Lie algebra.